Good evening.
Hello, sir.
Sorry I missed the last class.
I'll allow it for now. Everybody gets one.
And I remember what you said the first day. The first day of class, and I was like, he's right. I might as well not.
Brutal. All right. The weather sucks out there.
Anyone in the classroom yet?
Not at the moment, but one showed up. I think it's only gonna be one or two today.
Oh, really?
Yeah. Joe's not coming. He's got to work on his car or something.
I had that pretzel pizza.
Yeah.
Oh yeah. That so hits different.
It is life-changing.
Oh yeah.
Welcome back.
Welcome back. So like when classes are over, are they like gonna set us up with a test or are we gonna meet with somebody to see how that goes about or what?
So usually the way it goes is they check to see if you have enough hours for your post-assessment. So people who are just starting the process of everything, they're just taking the class. It's not enough hours because you need 60 hours minimum to be able to like post-assess. But once you're assessed to a level that you have a shot at passing, then you can always sign up for it. You can actually take like part of it at once, so maybe like the math part and then leave the English part for later, that sort of thing.
Yeah, like the high set version?
Yeah, so that's an option, but yeah, it's usually kind of hinging on the post assessment.
Okay.
So the classes alone won't give you the hours you need to take the post assessment, huh?
Yeah. And they definitely won't cover all of the material math wise. Like as it is, I'm like, if I had 4 times as much time, maybe even 3 times as much time, I'd be able to cover everything okay. But
So what if Okay, let's just say that we do have the hours and. Then we take like that little test or assessment.
Mm.
And it's still not at that level, like in classes or groups.
At that point, you have the choice of taking it again if you want to.
But the post test is not the actual test.
No,
Okay, it's just like,
yeah, essentially, it's for us to be able to gauge where you are.
okay.
It also says, you know, if you get any skill gains or anything, if everybody gets skill gains, then it's like, okay, you're kind of a competent instructor. But if nobody gets skill gains, then I'm incompetent. You know. Which might be the case for a lot of contexts, but you know, we'll see on this one. I think we can wait another couple of minutes because, you know, grand total of 3 isn't the biggest poll I got.
That's around.
I'm awake. I'm awake. I'm awake. It's a long week.
Yeah, been driving.
Yep. Had a couple of the busiest shifts at work I've ever had. So,
Is that a good thing or a bad thing?
it's a good thing for the center and a bad thing for how lazy I want to be. There's always a little give and take there, you know.
The old famous catch-22.
Yeah. As I was saying earlier, I wish I could just make an income without having to do anything. Or, you know, that life didn't require money to exist.
Like back in the day when you could just trade,
Yeah, right. We could barter.
right? I would so trade my kids.
That's fair.
Joking.
I wouldn't trade for them.
Not even those slave workers? Come on, dude.
I tell people they'd be good for manual labor and, you know, usually I was joking and now there's all kinds of states around the country that are passing laws to allow child labor, so.
No
Yeah.
way.
Yeah, you haven't heard about that?
No, I have not.
Yeah,
We're okay with child labor now?
some people are, yeah.
Wow. So that changes everything about the Jordans.
Let's see.
I wasn't sure how that joke was gonna go.
Here's one yet from yesterday. Iowa lawmakers passed legislation to roll back child labor protections. Let's see, so the governor expressed support for the measure that allows 14 and 15-year-olds to work 2 additional hours per day when school is in session from 4 to 6 hours. So that's not too bad, but oh my God, I forget what the there was one I saw where like the governor or whoever was signing the bill was signing it and, you know, making a big photo op of it. And there was just a bunch of depressed looking kids standing next to her. I'm like, this is clearly not a good thing.
It was probably the freaking mayor in Hawaii.
Maybe, I don't know. All I know is we can't talk smack on China no more.
No, sir.
Well, maybe for human rights violations, but definitely not child labor laws. We're apparently cool with that now. They found some 10-year-olds working. They found some 10-year-old migrant workers working in a McDonald's. That was fun.
Oh, wow.
Yeah. But
Damn.
yeah, technically, we actually have, small migrant children working all over the country. Just they got caught. All I know is I don't speak kid. I'm very confused when kids try to talk to me. I'm like, hello, tiny human. I don't get it. Seeing parents talk to their kids, and I'm like, how are you translating this?
Oh, that's up to you. Up to you, Mom. Yeah.
Okay.
All right. So,
Hello.
hey,
Bueno, pues,
that was a bold and proud hello. I like it.
hello.
Mhm. All right, so today we got more exponent stuff, and then
More
we got
ex-
roots. We like roots. We like exponents.
More exponents.
If we get far enough, we get scientific notation, which I already have prepared, which may be its own class or half of a class. But it's better to plan ahead for these things, All right. So, retreading water, we have exponents. They're shorthand for repeated multiplication. So 5 cubed, 5 to the third power, is 5 times 5 times 5. It's often written with a caret symbol, which is one of the many buttons you'll find for it in a calculator. So in terms of second power, it's often referred to as the square of that term, and that's pretty much it for what an exponent is. Now, multiplying them is one thing that we already did cover. Now, for these ones in particular today, I don't have any examples made for them because we kind of put that together pretty quickly last time. And I wanted to get into the newer stuff. Last time was totally wasted a lot of time last time. So multiplying exponents, if you remember, if you have something with the same base, so in this case we have 3's raised to different powers. If you're multiplying them together, you just add the powers together because it boils down to I have 3 this many times and then I have 3 this many times. So if I'm putting them together, then I have 3 that many times. I have 3 of them and I have 4 of them. So I have a grand total of 7 of them. And as I have down there at the bottom, if they don't have the same base, like 3 cubed, 2 cubed, you can't put them together at all. You would have to, like, if you're trying to get just one solid number for that, you'd have to work it out.
Yeah.
Okay.
I am sorry though. About being here.
All right. So here's new stuff. So dividing exponents. Dividing exponents actually isn't bad, just like multiplying wasn't. Multiplying, we just added the powers, right? So if you're dividing exponents, it's along the same lines. If multiplying goes to adding, then it would make sense that division goes to subtraction. So in this case, we have 2 to the 5th over 2 squared. What you do is you take the top power and subtract the bottom power. So 2 to the 5th over 2 squared goes to 2 to the 5 minus 2. So it's just 2 to the 3rd. At that point, you could either leave it 2 to the 3rd or turn it into an 8, whatever you want to do. But that's pretty much it. There is to dividing exponents. It's not so bad. Just the top power minus the bottom power. Now, I'm not going to say it's going to happen at any time in the near future, but these can get complicated. They can, once you hit these in algebra, there's all kinds of big, hideous messes that I've seen with these. And doing it this way doesn't really mesh well with my brain when I have more than 1 or 2 terms on top or bottom. It gets messy. There's a lot. I've had them where there's like 6 or 7 things, like, A through D, and then a bunch of numbers everywhere, and everything is different powers and what have you. And this isn't the best way to do it, in my opinion, when it gets trickier. So I did make a slide on how to deal with that. And this is just the way I like to visualize these, because if you know that you have 2 to the 5th over 2 squared, that's 5 2's on top of 2 2's, right? Well, they would cancel. If I have 2 over 2, it cancels. So technically what we're doing by subtracting is we're saying, oh yeah, one of them will cancel out one of them here. One of them here will cancel out one of them here. So in this case, you see me crossing out some 2's, then we just have 3 left. So you still have the 2 cubed. That's how I personally like to visualize them. And if you can see it that way, you can usually just kind of go straight from the initial question right to the answer. Because you can look at that and say, oh, I have 2 to the 5th over 2 squared. 2 are going to cancel from both. So I'll have 2 cubed on top. I won't have anything left for the bottom. It's a nice way to look at them.
Am I supposed to? What are we doing about 7?
What are you doing about it?
Goes to school,
I don't know.
and I get on, I'll take my friend of ours.
All right, so I got a bunch of examples, and you can see that some of them are uglier than others.
I thought Natasha was going to work before.
No, but she goes to work,
Yeah, after, yeah.
Thursday and Friday, she goes.
Hey, look, a mute button. All right. So I'm gonna write these out real quick. You like my number 3, 5 to the 106 divided by 5 to the 92? If that was actually written out, it would be the most horrifying thing you would ever see, but it's stupid fast with this. Then number 4, I'm just writing what's in the parentheses. That first parentheses on top. And then what's in that bracket, I'm putting
On the bottom?
on the bottom.
Okay.
But I'm dropping the first parentheses in the brackets. I just have that there to kind of separate them out that way. So it looks like that.
Okay, the parentheses will need to be there.
Yeah, because the parentheses, if I have it written out like that on one line, for instance, if I punched this whole thing into a calculator that could handle typing the whole thing into a calculator, you would need that parentheses because you'd have to be able to say, oh yeah, this whole thing is being divided by this whole thing. Otherwise, the way that calculators interpret everything, it would probably multiply this, multiply by this, and then it would divide by that. And then whatever that is, it would multiply by this 3 to the 4th. So it would just blow everything up. So when it comes to punching things into calculators, I've always erred on the side of caution and had more parentheses than I need to sometimes. Like if there's more than one number there, I put a parentheses around it. That's usually a safe bet. Okay, so number one, we have 8 to the third power over 8 to the first power. All right. All you gotta do, they have the same base, write it out once and do the top power minus the bottom power. So just 3 minus 1, we get 8 squared. From this point, we don't really have to do anything. If the instructions say to, break it out of exponential form, you could square it and say it's 64. Personally, I'm perfectly fine with leaving it that way. I like it, it's nice, and it gets the job done. It covers what we need to cover, what we need to understand, which is literally just breaking down these powers. Now, number two, same sort of idea. We have 2 to the 18th power on top, and we have 2 to the 14th power on bottom. So this thing is going to equal 2 to the 18 minus 14. So again, just top power minus bottom power. Which 18 minus 14 is 4. So we get 2 to the 4th and call it good.
That's it.
That's it. Now how does 3 look?
I don't know yet. It could be pretty hard.
No, like I said last time, it doesn't matter how complicated these problems get. I could have like a 40-digit number raised to the power of a 5-digit number over that same number raised to a 10-digit number. It doesn't matter what the numbers are, the rule matters. And it's always going to apply at all times. Like I say, things scale up. If it works on this 8 to the 3rd over 8 to the 1st, it would work exactly the same on this 5 to the 106. It's just going to be the top power minus the bottom power.
All the time,
Yep.
or when, at least when you're doing these.
There isn't some magical way that I could interpret it a different way. This literally means I have 106 fives over 92 fives.
Was it 106 or 105?
Yeah, that's a good question. I don't trust me. It is 106.
Okay.
106 and 92. Okay, so we have 5 to the 106 over 5 to the 92. That literally just means I have 106 of them here over 92 of them here. So the idea is kind of like that one slide I showed you where I like to think of it as them canceling. If 92 canceled from here and from here, what would I have left? Well, it's literally just that subtraction, right? So 106 minus 92. If you're rough on subtraction in your head, I usually tell people start from the bottom one and add up until you get there. If I added 10 to that, I'd be at 102, add another 4, I'd be at 106, so 5 to the 14th. And that's it.
So basically the 5 is obsolete.
I don't know what that means, but no.
It's just transferring over. You don't need to do anything with it. You don't.
Yeah, it's not something special. That could have been a picture of a foot for all I cared. If I have 106 pictures of a foot over 92 pictures of a foot. One, someone should delete my browser history when I die, and 2, yeah, same math. I don't like feet are gross. I feel like I need to say that out loud now. All right. But yeah, that's really it. As long as it has the same base, then you're good. Now number 4 is a little trickier because I have multiple things stacked up together, right? But all you end up doing is you end up doing the top power minus the bottom power. Now this number 2 doesn't have a power. So you just ask yourself, how many of them are there right there? 1, right? You can always just put a little 1 there. I didn't need to put a 1 there on number 1, but I have it there just to illustrate that, hey, this is 1/8. So this is 1/2. So when I split it up, I would do a 2 and then top power minus bottom power. But since these are all multiplied together, essentially, this next one is going to just be right up next to it, multiplied together. Top power minus bottom power, 5 minus 4. Yeah. So you do the subtraction. 5 minus 4 is just 1, so I don't need to put an exponent on that. And if I'm leaving in an exponential form, that's all I need. If I wanted to put it into a regular number, I could just work it out. But it doesn't particularly matter at this point. Like on
So
that last one.
We
Oh, sorry.
don't need write the 1 there on 3.
On the
Because-
3 now.
No,
No, because we don't actually need to ever write an exponent of 1. Because if you put an exponent of 1, all that means is that you have 1 of it.
oh, okay.
So we don't really need to say there's 1 of it because there it is.
Oh, okay.
Yeah. But I like leaving things in these exponential forms because if I don't, and I found 5 to the 14th, it's apparently 6.1 billion. Like that's a pretty solid number, right? So, you know, that's pretty much it for these. They're not bad. Now, for example, just as a random example, if I had, say, 2 squared over 3 to the 5th, would I be able to do anything?
No. Because they're the same.
Yeah, the bases aren't the same. So I can't do anything with that. All I could really potentially do with that is, you know, multiply out the numbers. And this would be a 4, and that would be 243. And 2 doesn't fit into 3 at any point. These are both prime factors, so I mean, that's all you could really do. But if you're leaving everything in exponential form, you would look at them and say, yeah, no, that's the question and the answer. We're done. There's nothing I can do to that.
Where'd you get 243 again?
3 to the 5th.
So 3 5 times.
Yep.
Okay.
3 times 3 is 9. 2 more of them is another 9. So 9 times 9 is 81. And then there's another 3. So 81
Okay,
times
that's
3.
right.
Yeah, because I absolutely,
So
Yeah.
you wouldn't just be like 3 times 5 is 15, you would have to literally be like, okay,
You-
3 all the
yep.
way through 5 times, like.
and that's actually an important thing. I actually have gotten that question a lot. You will never multiply this number by its exponent.
Okay,
Yeah, those don't mix. Exponent with exponent, you can kind of put together. If we're adding,
so it would be 3 times 3 is 9 times 3.
now you could do that and then multiply it by 3 and whatever that is times 3 and whatever that is times 3.
It would
Or-
turn out the same.
Or I totally like to do it this way,
Okay,
because I know what 9 times 9 is.
okay, you know,
Yeah. So you could just kind of piece things together in a way that's not quite so rough. Okay, so how do we feel about subtracting exponents?
we will have to see. It's making me tired. I'm just kidding.
That's the spirit. Well, if you'll feast your eyes on numbers 5 through 8, you'll notice that we have the word alone above them. Let's Let's do a couple. You like that idea? You all like that idea. You don't need to lie. So I'm gonna leave those up on there. And I'm gonna try to shut up for 6 minutes. As usual, it's gonna be difficult for me. And if you have questions, let me know.
Okay.
Wait, okay, the last one, the dot, does that mean multiply?
Mhm.
Okay. So the last one is pretty much as the same
like the last sample we did?
Kind of, yeah, it's pretty close to number 4.
Okay. Number 4. I got it.
All right, so how do we do?
I think I did mine, I'm unsure of the last one.
Okay. I'm gonna write down what they are real quick, because normally I do that before, but that would have made sense. That would have made sense. Okay, so a little basic on some of them. First one should be 3 cubed. Number 6, the answer is 2. Number 7, the answer is 7. And number 8, it's 2 squared, 7 to the 14th.
I got it right.
Okay. How did we do, everybody?
So for 6 and 7, because obviously like the round was 2 with the 1, we don't have to put the 1 because it's gonna equal 2.
Yeah.
Okay.
Yeah, exactly. You don't need to put a 1 as an exponent. If you have that as like a middle step, if you're having to like show your work or something, if you have that as a middle step, then it's fine. But you don't want to like have a 1 as an exponent, circle it and turn it in anywhere.
Okay.
Because it's just one of those things where it's like, yeah, you can have it for illustration purposes, but it's not really there.
Okay.
Does anyone need to see any of them worked out? Or are we feeling good?
I think for me, just number 8, please.
Yeah, so 8 wasn't a problem. That one was, I mean, technically they're all problems, right? That one was 2 cubed times 7 to the 15th over 2 times 7. And I mainly had that one to illustrate what happens with the, what happens when there is no exponent. And that's because you're supposed to look at these as if there's like a phantom 1 on top of them. So when you separate them out, kind of like we did up here on number 4, when you separate them out, you're going to do the 2's, and you're going to say the top power minus the bottom power. Well, the bottom doesn't have a power, but you're going to go ahead and write 1 because you have one of those 2's right there, right? And the same thing with the 7's. The 7's on top, you have a 15, but on the bottom, you don't have anything written. So again, there's 1 7 there. So you're going to subtract that 1. Then you do your subtraction. 2 to the power of 3 minus 1 is 2. And 7 to the power of 15 minus 1 is 14. And that's where that comes from.
Okay.
Does that make a little more sense?
Yep. Thank you.
Anytime.
Yep.
All right. We okay with moving on a little bit?
I think so. think so.
Cool. So we still have a little bit more for exponents, or we take a look at roots. So the first ones are exponents with powers on them. So, well, what happens when you have a to the 5th and that thing in parentheses to the 3rd power? Well, what you end up doing is you multiply the powers together. Now, the reason for that is because say if you add x squared to the fourth power, since that fourth power is outside the parentheses, it's saying that you have x squared multiplied by itself 4 times, right? That's what the outside, that 4 exponent's telling us, is that, hey, whatever we have there is multiplied by itself 4 times. In this case, it's something that already has an exponent. So if I multiply them all out together, x squared times x squared times x squared times x squared, then we have the problem of, hey, we are now multiplying these guys together. So what do? We add the powers, right? There's 2, 2, 2, 2. So we ended up with 2 4 times, so it's 8. And think about what I just said. I had it 4 times. Well, that's multiplication, right? Since I have this multiplied by itself 4 times, I can just actually multiply the powers together, the 2 and the 4. And when I multiply the 2 and the 4, what do you know? We end up with the same power. So whenever you have that sort of example right there, where you have something in parentheses raised to a power, even if it has multiple terms inside, what you're going to end up doing is you're going to end up multiplying that outside power, that 3 in this case, to every power on the inside. So if there's multiple terms, that's what happens. But that's pretty much it for those. They're not bad. It's just, you know, I made some ugly ones, but you know. It's just when I have been teaching this or tutoring exponents in general, the things that I see people mix up the most is when you multiply the powers and when you add the powers. And the main thing to keep in mind is that when you are multiplying powers, it only happens in cases like this, because if you look at number 1, we have 2 cubed twice. Because that's what that exponent means, right? So that's how you think of it as being multiplication. When it comes to addition, that's just us taking a bunch of stuff multiplied together and slapping it on top of another thing multiplied together. So in that case, it's 2 distinct things. In this case, it's one thing to a power.
So what is the purpose for the double parentheses?
Well, it depends on which one, but largely it's just to separate things out. Anytime you see multiple parentheses, that's really all they're doing, is making sure that you can see what's grouped together at any given time. Like on number 3, for instance,
There's like the parentheses and then there's like the one right next to it.
yes. So if you look at that, look at as kind of opening and closing parentheses. You're opening 2, and then after that first power, you're closing 1, and then you're raising that to a power, and then you're closing the other one, and you're raising that to a power. So what's happening there is that 3 squared is getting squared, and then whatever that is also getting squared. So it's kind of messy, but it's not too bad. So the first couple are pretty basic, right? After we've gone through that, we know, okay, that we have, when we have a power on the outside of a set of parentheses, we are going to multiply that power into it, right? So that's going to multiply onto the 3. And these ones, I'm going to go ahead and write it this way, where I'm multiplying the powers. You don't really need that step necessarily. You could look at this and say, oh, 2 to the power of, well, 3 times 2 is 6. So you just say equals to the 6th. That's fine. I just want this here for illustration purposes. Okay. Same thing's happening on number 2. We have 3 squared and it's being squared. So that means I have 3 squared twice. Okay, well, no matter which way I want to look at it, I could have 3 squared times 3 squared. I would have plus 2, 4. Or I could have 3 squared squared. So I would have 3 to the power of 2 times 2 is 4. That's it. That's why the other ones are so complicated looking. Because these ones are quick, right? Yeah, no, yeah.
Okay, hold on, I need to backtrack a little bit. Okay, so. 3 times 2, or 3 to the second power is 6, right?
No,
Am I saying it wrong?
you're thinking multiplying those numbers again. What does that 2 mean? It means that you have that thing multiplied by itself that many times. So if I have 3 squared, that is a 3 times 3.
Okay, so that's 3 squared is what's in the parentheses, right?
Mm-hmm.
Okay, so the 2 outside of the parentheses. Wouldn't that be? Whatever the 3 squared equals times 2?
Not times 2. Remember, exponents, you're not just multiplying numbers out.
Okay,
This one right here means that you have 2 of these 3's multiplied together.
okay,
This one right here says that you have 2 of this whole thing multiplied together. This thing is equivalent to saying I have 3 squared times 3 squared.
okay. And 2 times 2 is 4.
Yep.
Okay, I see. Thank you.
Yeah, and if you did it this way by expanding it out, you'd add them up, which again, 2 plus 2 is 4. So it'd work out either way.
Okay,
Now, those are, as long as you can see it that way, they're pretty quick. Which is why I made the rest of them kind of horrifying. That was completely intentional, because if you can understand these, you'll be able to understand any of them. Have I ever actually seen a problem like number 3 on a test? No, I have not.
but
Did I-
it's good to know.
It's good to be able to understand it, because if you look at it, it's the same thing as this last one with another set of parentheses, another 2, right? Like that right there, that 3 squared squared is number 2.
Okay,
But all we're adding is another level of it. So what is happening here? Well, we have 3 squared and that's being squared. So now we have 4 of them, right? We just figured that one out. We just have, this is 4 of them right here. But then it's inside of a parentheses as well. And it's also being squared. So we have 3 to the 4th happening between these 2 pieces. So 3 to the 4th squared. So I can look at it as 3 to the 4th times 3 to the 4th, where I'd add the powers, or if I have this 4 right here, I can just multiply it right here, because we're saying, yes, I have 3 4 times, but I have that 4 times twice. And that, you saying twice, I have it 2 times means that I can get away with multiplying it. So you just multiply it together, you have 3 to the 8th.
okay.
So power outside parentheses, multiply. Now we have something different on number 4. Number 4, we have multiple things inside that set of parentheses. Now I'm trying not to have too much algebra before we hit algebra, but having little bits of it's pretty nice, and also there's no way for me to illustrate this point without having a couple of letters in here. So that's the only reason I have an A and a B. Those are two variables. It's some number squared times some number to the fifth. I don't care what the numbers are, not in the slightest. I guess I could have made it like a 2 and a 3 or something. I don't know. It doesn't matter. We got an A, we got a B. This one's squared, this one's to the fifth, but we have a 10th power. What do we do? Am I going to write out this thing 10 times and then add up all the A's and add up all the B's? No, that sounds awful, right? So it follows the same rules that all of these did up here. 2 to the third squared, well, we just multiplied the 3 and the 2 together. So we had 2 to the third twice, so we had 2 to the sixth. Not bad, right? So reasonably, if I have this thing 10 times, that 10 is actually going to kind of distribute to each individual exponent, as if they're each their own problem. A squared to the 10th power, well, I have 2 10 times. Well, that means I would have 20, right? And then with the B's, I have 5 of them 10 times. Well, if I have 5 of them 10 times, 5 times 10, that one's going to be 50. And yeah, that's it. Sorry, it's not more complicated.
No, you're not.
I mean, a little bit. I couldn't make, huh?
Did you say number 9?
What? What's happening?
I was confused, never mind.
Okay, me too.
I had it going over.
I actually don't know that I could make this more, well, I could make it a little more complicated.
You could,
I could.
100%. I've seen you do it.
Maybe I'll make up one horrible one after this next one, just so you guys could see how horrible these can get.
Is that really
Big bet.
necessary?
No,
It's not necessary, Robert, just.
yeah, she wants to get to the one she has to do alone quicker.
He won't do it.
See, he knows that that's gonna make my psychology click and be like, now I have to. Now, you'd think that I would work against that, but honestly, I just have more fun doing it. So what's happening on number 5 here is I have 5 squared times 25. Similarly to the problem we did with exponents on that, I turned the 25 to a 5 squared, and then I was like, okay, well, I don't really need to distribute this 2 into there because these guys can go together. So it's a 5 squared times a 5 squared. These guys, you would just add the powers together. You would have 5 to the 4th, because there's 2 of them multiplied together, multiplied by another 2. So we have a grand total of 4 of them all jumbled up.
Wait. Okay, so how did you get? How did 25 go so 5? It's because 5 times 5 is 25.
There we go. Yeah, so I turn that 25 back into exponents. Then I put these guys together by adding the powers. And at this point, you wouldn't multiply the power. When you have that power on the outside of parentheses, you multiply. So 2 times 4 is 8. Oh my God, he's doing it. Say I had. That's not horrifying.
I was just thinking that 100%.
Yeah, it's good. That'll do. I like it. There's a random example. It exists. So in this case, we have 27 a to the 5th to the 3rd power times b to the 4th all over 3 squared a to the 15th. Isn't it beautiful? Oh, your brain just shut down. Look at that.
I think it's beautiful.
I'm not writing it down, I'm just gonna listen,
Okay, that's probably for the best.
because then if I try to do all that, then it's just gonna make all this rest of the stuff we're gonna go away.
Okay.
Yeah, but imagine if you start writing it and it actually starts coming out.
Robert,
Children, please, I will turn this college right around. Park it back at home, make you sit in the driveway till you learned your lesson. No, I'll make you sit in the garage until you learn your lesson, but the engine will still be idling. So
You got a time limit.
you got a time limit. Cause that exhaust is coming out. All right,
Old fashioned gas cars.
yeah. There's some things that gasoline vehicles can do that electric vehicles will never be able to achieve.
Fucking A.
All right. Isn't it weird that we kind of like decided collectively that we were gonna have big things with wheels on them go really fast, and we're gonna power it with melted old dinosaur bones?
Right?
That's kind of cool. It's metal is what it is. All right, so here's what I'm gonna do. First thing is when I have something big and ugly like this, I usually kind of treat the top of the fraction as its own problem until I can, start putting things together between the top and the bottom. Like my first thought here is the fact that I really don't want, like, this cube is going to have to go to each thing inside of this parentheses, even that 27. Do I want to cube 27? No, I don't want to cube 27. So the first thing I'm going to do is break down that 27, because we know that 27 is 3 times 9, which is 3 times 3. It's a bunch of 3s. It's 3 cubed. Everything else I'm going to leave exactly the same. And then at this point, this is where I would look at this and say, okay, well, I can't really do anything down here because those just exist. Can't do anything with a B, that just exists. Can't do anything inside here because that just exists. The only thing I could do anything about is this parentheses with that 3 outside, right? So again, that power is going to multiply onto all the powers here. So I have 3 to the power of 3 times 3, 9. I have an A to the power of 5 times 3, 15. And then we have that B to the 4th. I'm not going to put the multiplication symbol there because the only reason I had it here was because it was multiplied by a big ugly thing. I can see that it's being multiplied together without the symbol, so I don't really need to write it. Well, now it sure as hell looks like one of those dividing exponents problems, right? And that's actually that's an application of these things. Sometimes you're going to have all of these rules all at once in one problem. It's going to happen. You're being given the small pieces to a larger puzzle most of the time. So here's what I like to do, because when I said that I really hated looking at things as if I am just separating them out and doing top power minus bottom power, top power minus bottom power. This is what I was thinking of. I was thinking of this because taking the 3s and the A's and the B separately as different little mini problems and then putting them all back together, that leaves some room for error, right? Like I feel like I could screw that up pretty good. So what I usually do is I'll look at this and I'll say, okay, well, I'm actually not gonna need that. Whoop. Well, okay, if I do this as the canceling thing, if I said I have 3 to the 9th over 3 squared, and I wanted to look at this and say, okay, well, this is 9 3s multiplied together. This is 2 3s multiplied together. They could cancel some, right? 2 of the 3s would cancel here, and 2 of the 3s would cancel here. If that's the case, how many would I have left right here?
They're back.
Getting rid of 2, right? So that's 7. And it ends up achieving the exact same thing as going to the trouble of saying this minus this. Okay, well, what about the A's? I have A to the 15th over A to the 15th. Gone. I don't care what A was. Yeah, I don't care what A was. I had 15 of them divided by 15 of them. They're all gone. Didn't matter. That B, anything with it? No, no other B's. Cool. Then it just kind of hung out with us until the end. That's it. So it looks like a big old ugly jumble, but what did we actually do? We turned this guy back into exponents so I could more easily multiply the powers together. And I just got rid of the parentheses. And at that point, I kind of canceled some stuff out and wrote out what I had left. And there we go. Oh, hey, I didn't box this guy. Isn't this fun?
That last one, no.
Okay, that's fair.
But the other ones are fine.
I've seen a lot uglier than that. I wanted to make it slightly uglier, but the canceling thing is going to seem almost like a necessary thing to understand once you're doing this with what's on like the next chunk of slides. However, it's your guys' turn. Yeah, look at that. I'm gonna give you 6 whole minutes to work them out. I believe in all of you. Oh man, an hour in, I have a total of 5. I have half the class that I did last week.
Is that a good thing?
No,
Oh, no, it was for people else.
Hmm?
Oh. I'm like,
yeah, I went down.
Like, did they email you or anything that they were gonna be back?
I've seen a couple of things where people are having tech problems in the last week or so. But I did have enough people join randomly throughout the night on Tuesday. And not so much tonight.
Yeah, but you gained a student that wasn't in last class this week, though.
That's true.
And what?
He wasn't here on Tuesday.
That's why class was a little boring last week, Tuesday.
No, Joe brought pizza. That was a good substitute.
Well, yeah, of course. I'm substitute for food, so it's all right.
That's fair. I keep rubbing my belly at work when people talk about somebody being fat, and I'm like, his name will be Jonathan.
Hi, Jonathan.
I don't know, because it's fun to say. He's mostly cheese. He's cheese and off-brand Coke. Love me my off brain.
I'm just gonna leave 3 alone because of this one.
It's extremely similar to the last group's number 5. I will throw that hint at you. How we doing, everybody? Has it been long enough? I really didn't look at the clock.
I need some help in number 3.
That seems to be pretty common.
Yeah, I tried to go just leave alone.
Are we ready to look at them?
Yes.
Okay, so. Number 1 is going to be 5 to the 6th. Number 2 is 2 to the 12th. Number 3 is tricky, so I know we're gonna look at that one. How do we feel about number 4?
I got W8 and Y12.
W to the 8th and Y to the 12th. So do we just need to see number 3, guys? Alright. So it's both extremely similar to number 5 and kind of similar to the top of the random problem I made up. So the main trick here on number 3 is that this 27, you're gonna have to break it down into exponential.
That, okay, I was somewhat there.
Yeah, so we end up with 3 cubed as that, which is then multiplied by a 3 cubed. And that whole thing, in fact, I'm gonna change it to brackets just so you can kind of see it separately. That whole thing is to the power of 3.
I don't know why I don't. I don't know.
Yeah, stop it. You
I
good?
was writing it down and then I'm just like, no. But it has to be that because 9 and 3 is 27, so it has to somewhat.
Yeah.
Yeah.
Yeah, so these guys right here are gonna multiply together, 3 cubed times another 3 cubed. We have 3 of them and another 3 of them, they're all multiplying together, so we have a total of 6 of them. And that whole thing right there, which is now a smaller whole thing than that thing, is raised to the power of 3. So that means I have this thing 3 times. So what we're going to do there is multiply the powers. We end up with 3 to the power of 6 times 3, which is 18.
So I have a quick question.
Yeah,
In your example problem and in this problem, you broke down 27.
yeah.
So the question is, in these advanced math problems, can you break down a number if it can be broken down? Can you break it down like that?
Yeah, I don't see why not. Like, say I had,
Say the number was 18. That's simple math right there. Would you be able to break it down and then get the same answer?
I would turn it into a 3 squared and a 2. And then that might fit with something else that's hanging out, or it might be that it's over something, you know, like that. And I might be able to cancel some stuff out all over the place. Yeah.
Yeah. No, I was just saying, like, if it was 18 instead of 27, would
Yeah,
you still
then-
be able to break it down?
Then that turns into, where are you stuff from last class? That turns into something like this one. You remember we took the 72, we turned it into an exponential form. That one broke down to 3 2s and 2 3s. So we had 2 3 times and 3 2 times. So you'd always break them down that way. So that's all we're really doing, is we're taking what we learned in the last class, and now that's a piece of these problems.
Okay. All right. So yeah, no, I was just curious
Yeah.
if you could, if it can be broken down, if you could break it down and get the same exact answer.
Absolutely.
Cool.
And then,
Thank
yeah,
you.
like, eventually you start running into them where there's one on top of another. And you end up cleaning them up the same way, and then you end up using the rules of dividing exponents, and it all gets put together.
All right.
All
Cool.
of the rules that I teach you apply all of the time. No exceptions. If it goes together that way, it can be broken down that way. And the nice thing is having 27 times 3 cubed, the whole thing cubed. I don't have to go to the trouble of figuring out that it's freaking 387 million. I don't care that it's 387 million. I cared about that 18.
Yeah.
That's the effort there.
Yeah, because that 18 is going to take you to the 387 million, but we're not there yet.
Exactly, and I'd rather write that.
Yeah.
And you're not gonna need to multiply that out. That's not a thing.
And just by looking at that, you can tell that that's what you're supposed to do.
Yeah, and when you get to the point where you're doing these types of problems and homeworks, it really boils down to sometimes you will turn them back into regular numbers and sometimes you won't. And it's kind of like a best judgment sort of thing. Like I like to tell people, hey, can you easily multiply out 3 to the 4th. Well, yeah, if your calculator has it, that's no problem. And if you were typing it 3 times 3 times 3 times 3, that's no problem at all. Would it be annoying to do an 18? Yes. Okay, cool. You're leaving it. That's usually what ends up happening.
Sounds about right.
Yep. So, and then you get high enough and you start getting to trickier stuff with algebra stuff in it, and they're usually using smaller numbers. So it ends up not being an issue anyway. Because the idea there is that you understand the method, not, nobody cares if it's a big number or not. People care if you get the understanding of the idea.
Okay.
So. Why are we all feeling so negative?
Because we're about to do negative exponents.
Negative exponents. What happens when you got a sign up there? Not a whole lot. Not a whole lot. So I like to explain it as, if you're thinking about what an exponent is, an exponent says how many times a number is multiplied by itself. So if you have 2 cubed, that says that it's 2 multiplied by itself 3 times. So what happens if you have a 2 to the negative 3? What's the opposite of multiplication? Division. So negative exponent is basically saying how many times you divide by that number. Now, you're not really going to need to understand that concept. What we're going to do is, instead of thinking of it as dividing a number, it's kind of like when you divide a fraction by a fraction. You just don't, right? You put it into a term that you can work with. And this is how we do that. And this is my personal way of explaining it. I prefer it this way. They have different ways in every math book I've ever seen. But I always just tell people, hey, if you want to make a negative exponent positive, all you do is you move it to the other side of a fraction. So if you have 2 to the negative 3rd, you just change that to 1 over 2 to the 3rd. If you have 1 over 7 to the negative 5th, you just turn that into 7 to the 5th on top. That's all you really need to worry about. Once you take care of that, then do the math stuff. As I have written there, it isn't recommended to try to perform any operations with negative exponents. So take care of them first. Make them positive. That is going to make your life easier. That's that's those. That's it. So let's look at a few. Of course I had to have a mess one. You know me, I had to have a messy one. So all we're doing for these examples is cleaning them up. That's it. So I'm not going to need a lot of space for this. Okay, I need a decent amount of space for number 3, but other than that. Okay. All we're doing is returning these into regular things, regular positive exponents. That's all we're doing. So all we have to do is look at this and say, okay, well, I have a negative exponent. So the way you make it positive would be to flip it to the other side of a fraction. So since you have a negative exponent up here, it's going to become a positive exponent down there. What? Huh? That's it. It's literally just, hey, here's the thing. Please try to understand this thing. We have 2 to a negative power. Cool. all I care about, that negative power, put it on the bottom of a fraction, make it positive. As it. Now, again, this does have a lot of applications to it. I'm gonna do number 4 before I do number 3. I probably should have made that one like the last one. This does have a lot of application to it. This can just naturally appear in some of your problems where you end up with a negative exponent somewhere. If I had any of the previous examples before this, with the division flipped upside down where the power on the top was smaller than the power of the bottom, we would have ended up with a negative exponent every single time. So we actually, I'm going to do probably a couple of examples just so you can kind of see that, because I kind of wrote this over the last 2 hours, so you know. So like something like that, that would be, sorry guys, this is me realizing that I have really crappy examples today.
You said it, not me.
I mean, I say a lot of things, so yeah. Okay. So I'm going to do these. I'm going to use these as a lead in to number 3 over here. I think I actually, yeah, I literally separated out. I literally just separated out the problems that I had written originally because this class was written in a lecture sort of way where I did not actually make you guys do any of them. And then I've been going through and separating out all the problems. And I absolutely did not separate these properly. Let's do.
I think you did fine.
I did now that I'm adding these extra couple of examples. Cool. So these two, pretty quick, pretty easy. Number 4, we have a negative in the exponent, but it's in the bottom. So to make that positive, we have to bring it up to the top. If I bring it up to the top, there's nothing down there anymore. So we just don't really have to write anything. So it's just a 7 squared, right? It's not so bad.
If you brought it to the top, wouldn't that make it 17?
No, that's not a 10 and it's not adding to a 7 squared. No. I'm just gonna say no.
Well, there's a 1 right there.
Don't care. It's placeholder. I have 1 out of 7 of the negatives 2. Care. See, now you feel like you asked such a ridiculous question, but these are questions that I think at some point or another in my life I have gotten asked. So such is life.
I'm just making sure that you're on your toes. That's all.
I'm not on my toes. I'm sitting in a chair.
That was a good one.
It's accurate. All right, so
It's legit.
random example number 1. I have 3 squared over 3 to the negative third. These are closer to direct applications. These are the sorts of things that when I made up that big, ugly, weird looking problem earlier, and I said, this isn't ugly enough. I really wanted to throw a few of these in there. I really did, because, or at least put a power higher on the bottom, because being able to understand how to deal with that, very useful. So there's a couple of ways to do this. And I'm going to show you the book way of doing it first, and I'm going to show you the Ben way. So the book way of doing things is to stick with the strict definitions of what to do with dividing numbers with exponents. And it doesn't change at all based on having a negative. The strict rule is still top power minus the bottom power. But if I was subtracting these, I'd be subtracting a negative number, right? I'd have 2 minus a negative 3. Well, what happens when you subtract a negative? It turns positive, right? You're taking away a debt. So when you subtract the negative, this ends up adding, you end up with 2 plus 3, 5. Now that's one way to look at it. The other way to look at it is the, well, Ben is lazy and prefers to just move stuff around way. If I have 3 squared over 3 to the negative third, and I want to clean that up, well, what have I been doing so far? If it has a negative exponent, I move it to the other side of the fraction bar, right? I already have something there. So you know what's going to happen to it? It stays there. And then this guy comes up and it's just going to hang out. So that thing with the negative exponent is just going to jump up here. Now multiplying these together follows the same rules we've learned so far. We are now multiplying things with the same base, which means we add the powers. Either way, you're going to end up with 3 to the 5th. Which way do you want to do? Depends on how ugly the problem is. If it's as simple as one thing over another thing, all right, that's no problem. I don't mind doing it this way. But if I have a horrible jumble of different things, hint, 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 I might want to look at it as make all my stuff positive and try to cancel stuff, right? Likewise, there are similarly 2 ways of doing this one. I could do, again, top power minus bottom power. Change that to a plus. Negative 2 plus 5 would be 5 to the third. The other way to do it would be to move things around until all my powers are positive and then clean it up. So if I did that, this 5 to the negative 5, it's negative on the bottom, which means if I bring it up top, it'll become positive. What's already up here? Something with a negative exponent. Well, if I have a negative exponent on this one, it'll become positive if I bring it down. So they kind of switch places, right? And then if I looked at it any way I wanted to, I could do the top power minus the bottom power, 5 minus 2, still going to be a 3. I could look at it as canceling these guys. So 2 would cancel from here, 2 would cancel from here. I would have 3 left right here. No matter how you look at it, you are going to end up with 5 cubed, no matter what. Okay. I've written a bunch of stuff under where I was going to do number 3, so I'm going to just do that over here now. Now I've said a sufficient amount of things to be able to reasonably walk through this one. Because if I had just done those first 3 and started talking about this one, that would be a little all over the place. Number 3, here's the big ugly. Let's look at how to do big ugly. So big ugly, we have 2 to the negative 3 times 3 to the 5th over 2 times 3 to the negative 4th. Now, the way I have it written here, I have just 2 multiplying onto the parentheses, but see, this is still just a thing times a thing. So I could have dropped the parentheses and put a multiplication symbol here. If this had had an exponent, I could have just stacked them next to each other because the multiplication would have been implied. I could have done a lot of different ways of writing this, but all I got to worry about is this is a thing times a thing. Okay. Now, like I said, there's a couple of ways to do them. You could split it up and do this is one part and this is one part. So top power minus bottom power and top power minus bottom power. And that would work. Well, let's see what happens if I do that. All right, let's see what happens if I do that. So if I split it up that way, I have a -3 up top, and I would have to subtract, well, I have 1 here, right? Then over here with the 3's, I have a 5 on top, and I'm going to subtract a -4. So this will turn into a plus here. I end up with 2 to the -4th. And then 5 plus 4, 3 to the 9th. Well, now what do I do? Well, we have a negative exponent. So the only way we can continue is if we take that negative exponent and bring it to the bottom of a fraction. Now, personally, I'm not a big fan of doing it this way. Because like I say, everything that we do at this point gets built upon, right? All of these rules are going to apply all of the time. And I have done a lot of problems where I end up with a bunch of different stuff over a bunch of different stuff. And sometimes I'll have different numbers, sometimes I'll have fractions here, fractions there, decimals everywhere. And how you split them up gets a little ambiguous. It gets a little tricky. So especially if I have nothing but variables happening here and then numbers out front, then it gets kind of weird and I end up having a fraction. I got to remember how to split the fraction. It gets weird. So that's why I kind of came up with that canceling way of doing things, just because, at least in my experience, it has worked out very well. And it kind of, no matter how complicated a problem has been, it has always worked. And it has always been easier to look at. And that's what I prefer. I like things to work. I like them to be easy to work with, easy to look at, make life easier. So what I usually do when I have a big pile of a bunch of stuff is I look at the ones that have positive exponents, because I know I'm not going to do any math with this stuff yet. I'm just going to make powers positive. Okay. Anything that already has a power it's positive, I'm just going to leave as is. At this point, I'm just sorting stuff, right? So I have a 3 to the 5th up top and a 2 on the bottom. I don't care that this was first. Not even a little bit, because two things are multiplied together. It can multiply together in whatever direction it wants. Now, anything that has a negative exponent on top, I'm going to bring to the bottom and change to a positive. So this has a negative exponent up here, that 2 to the -3rd. So I'm going to bring it down here to become positive. I like to put symbols, multiplication symbols next to anything that's just hanging out alone. That way I don't think this is a 22 to the 3rd. And then this guy down here, this one has a negative exponent down here. So if I bring it up there, it'll be positive. And I still have roughly like the same thing, but now I can see better that these 3's will just stack together and turn to 9, and these 2's will stack together and turn to 4. Now, which way is easier? Honestly, it depends on the problem. It depends on a lot of different factors, how comfortable you are with one way versus another way. Just depends. But you could go either route. Do we have questions on these? On any of them? Questions, comments, concerns? Slightly mentally checked out?
Yes.
Okay. You know, I was mentally checked out earlier when I was doing people's venipuncture.
Venipuncture,
Yeah, and I was putting the needles in people's veins because I work as a phlebotomist. Yeah.
where's that at?
Huh?
Where's that at?
Over at the biomat by Target.
Oh,
Yeah,
I just got to like up in Bell.
yeah, plasma donation.
Yeah.
Yeah,
I've done it once, but like, the guy let me in when like my levels were just like a point under from where it should have been. Not a point, but like a percent. Basically, like my iron was just so low,
okay.
but they let me in anyways. The second time I tried to do it, they're just like, no, you need to eat more meat or.
Yeah, there should never be a, I'll let that slide. Like ever. Like,
Really did.
well. If I knew that, I knew who it was, I would slap them. That could cause problems.
But they keep calling me back to get blood, so
Uh,
maybe because I need the blood.
it helps. They just changed the donor pay scale, so yesterday was the busiest day since last summer.
Right.
Like there's so many people. We went through 98 donors yesterday,
Oh, shit.
and it's usually been closer to like 60 to 70 a day lately. So, yeah, once I got there, just constant the whole day. Yesterday, not a whole lot went wrong, so it went pretty smoothly. This morning, lots of things went wrong. So it didn't go as smoothly and we got backed up. It was great. All right, everybody. Hey, look, we have a bunch of them for you to do alone. Aren't you excited? You guys don't sound excited. Tell me you're excited.
It's like Friday, so
We are so excited, Mr. Ben. We cannot hold ourselves from screaming with joy.
Okay, well, I don't want to witness you holding yourself, so do whatever you gotta do.
what the heck?
Do the math, do the math,
I think Robert's trying to come with it because it's so quiet right now.
Gotta make it safe for school.
Neither here nor there.
It's kind of funny because you're there and I'm here.
Uh-huh.
Yeah. I want it to be my Friday. I'm doing 6 days in a row.
It's
7.
4 day for me for work and stuff like that.
It could be argued that it's a 7-day for me because I have a meeting I have to go to on Monday and it's not optional.
So is number 3 supposed to be that highlighted?
That one was made with a pure black color in a different app. So it's literally just an image that I inserted in here.
Okay.
All of these ones are not pure black. So every time I turn these into pure black, I kind of hate it. Yeah.
Yeah, they don't look the same.
Yeah, I don't like it. So yeah, that's what's going on. It looks significantly more different on my computer at home.
You can bring your kids here.
Yeah. I've had people bring kids. I don't care as long as they're not disruptive. Sometimes when they're disruptive, I'll make them do math double. I regret nothing. It's been 5 minutes. Okay, I don't know what, I don't. How we doing on these guys? How we feeling?
Could we check the number 8?
Be 5 squared.
5 square.
Yeah. So I'll write down what they are, and then if you guys didn't get those, then we can work them out. Okay. So 5 through 8, 3 to the 4th, 2 to the 3rd, 1/7, and 5 squared. How do we feel about this? How does it make you feel? Tired? Me too. Does anybody need to see any of them worked out? Is everyone checked out?
Most definitely.
How about those of you online? Are we checked out? Are we checked in? How are we feeling right now? And yes, I am looking at the chat box as well.
So on 7, we just you have 1/7.
Yes, sir, because we have 7 to the 4th over 7 to the 5th. The reason that this counts as a negative exponent problem is because if you do it as the division method, dividing numbers with exponents, you would do the top power minus the bottom power.
Yep.
So you would get, and yes, I know I wrote that horribly, you would get 7 to the -1. And that -1, you would bring that down to the bottom of a fraction bar to make it positive. You don't need to put 7 to the 1st. You could just write it as 1/7.
Gone. And to the 7. Okay.
Does that make sense?
Yep. So well, that's fine. Okay.
Okay. Everybody else good? Good? Happy? We all happy?
Yes, thank you.
Everybody's real quiet tonight.
We are fine, thank you.
The chat's
I'm not
dead.
fine.
Chat's dead. I got one of you paying attention, right? Yeah, that's pretty good. Okay. Well, let's take a look at roots. After roots is scientific notation, but I like roots. So roots.
I like roots too.
I know, it was great. Kunta Kinte and everything.
Oh, I
Lamar
thought we were
Burton's-
talking about potatoes.
Okay, I was saying LeVar Burton's an amazing actor. You know the old miniseries Roots. Yeah.
Oh yeah,
Oh yeah, it was great.
love that. I was so happy when they brought it back.
Oh yeah, yeah. Look at that, Kunta Kinte. Yeah, we all need a LeVar Burton in our lives.
What the heck?
What?
Wait,
you never seen
hold on.
Roots?
Hold on. Reading Rainbow was
Yeah,
Kunta Kinte?
you didn't know that?
I had no idea. This changes my whole entire life.
Please tell me you knew he was in Star Trek at least.
Yes, he played the black guy. Yeah, yeah.
No way, he played a black guy.
No, you didn't let me finish before you pulled up the picture, so it's apparent. I was gonna say the sunglasses across the eyes.
Oh my god.
There's that.
No way, he played the black guy.
Oh my god, I love that sweatshirt he's got there. It's awesome.
Like he played Reading Rainbow for like 300 years.
He still does.
Does he?
Yeah,
They brought it back?
kind of there. It's still a big deal, but what they do is they kind of turned it into like a website, so you can watch parts of it with your kids and everything. And they were like, maybe this will work better on like a tablet sort of thing.
Oh my God.
Yeah, no, LeVar Burton's one of my favorite humans, like ever. Dude's awesome. Dude's like legitimately awesome. I love him. Amount of people who can say, oh yeah, reading Rainbow, that's why I like reading books. Really high. That butterfly was in the sky, but I could still go twice as high. All right. So Roots. God, I get derailed easy. All right, so roots are the opposite operation to exponents. So the symbol above a root is called a radical, and you can undo that a power with a radical, and you can undo a radical with power. Again, they're kind of, well, they're not really opposites. They're the inverse of each other. So square root is the opposite of square, cube root is the opposite of a cube, and it just scales up. It, fourth root, opposite of a fourth, fifth root, opposite of a fifth. Yeah. You know what's gross? Tonsil stones. All right.
What the heck is that? Is it like both muscles, like,
Tonsil stones. Those are fun. Yeah, because you got little openings in your tonsils. So yeah, you can totally get a buildup of calcium in them like kidney stones. Except they're easier to deal with because you just like poke them out, but they're gross. But I think I just swallowed one. All right. You're all welcome for what I just gave you. It was a gift of knowledge. Okay, so since we've been working with exponents, we can recognize squares and cubes more easily. It translates very well to the concept of square roots and cube roots. So if you know that 2 squared is 4, then that means the square root of 4 is 2, because you would look at that and say, what multiplied by itself is this number? That also works exactly the same with cube roots. We know that 2 times 2 times 2 is 8. So if I had the cube root of 8, the answer to that is 2. You're basically, you're chopping it up a little bit. So the method of breaking these guys down, what I usually do, like to explain it as, is you take out anything that's a perfect square with a square root. So if you look at the wonderful little image I've prepared for you guys, if you have the square root of 4, well, 4 is 2 squared. We know that's 2 times 2. That's a perfect square, right? So that perfect square would come out of the radical and just be a 2. So same sort of thing happens with a cube root. Cube roots are similar, same idea as square root. Square root, anything that's a perfect square, you have 2 of that factor, it can come out. Cube root, anything that's a perfect cube, you have 3 of that factor, it can come out. Now, notice how I am explaining that instead of explaining to you, hey, cube root of 8 is this number. Square root of 4 is this number. I'm referring to things coming out or, the power scaling up. The reason I'm explaining it that way is because I truly hate how roots are taught in most classes. I feel like, because you will get straight up like 2 pages of these problems. And then they'll throw in a couple of tricky cube roots to see if you can figure it out. And then they might do a bunch of cube roots after that. And then you're never going to see anything higher than that root. You might get, you ever have like a homework assignment and they give you that really tricky one at the end. And a lot of people skip it, but you can get that extra point. Something like this, it might be a 4th root, something like that. But the way I like to explain these guys is in such a way that it'll scale up all the way. Like by the end of this, if you use this method, you can absolutely do like 50th root if you had to. Like it doesn't need to be as bad as they'd like to explain them. So larger roots than square or cube. Things you're not going to see. You're not going to see this on a high set. You're not going to see it on a GED test at all. Not even a little bit.
Well, will we see some of them, or they're just saying?
Oh, you're gonna have roots on it.
Larger roots.
Yeah, larger ones. You're not going to see that. You're not going to have a 5th root. But the concept is the same. That's what I really want to get you guys to understand is the concept. If I have the 5th root of 32, well, 32, if you factor tree that all the way down, it ends up being 2 to the 5th. Hey, I got the 5th root of something to the 5th. Guess what? It's just 2. Or like how I have there, the 37th root of 5 to the 37. Well, cool, I have 37 of it, so it comes out. That's literally all it does. And there's actually, just as an illustration, just for that, this is why it works. This is also something they don't explain to you when you're learning it, and I feel like it helps. I told you that they're kind of the opposite, but opposite isn't the right word. It's kind of the inverse of an exponent. An inverse is basically inverted. It's flipped, right? So what you end up with is 5 to the 37. If another way to look at these are actually fractional exponents. I used to have these in my lessons, and then I realized that I don't think any of them are on those tougher tests. But based on what we just learned, if I have a power outside here, that multiplies in, right? Well, what's 5 to the 37 over 37? That's a 1, right? That's just 5. So that's why they cancel each other out, because these guys are actually kind of fractional exponents, which is why we cover them at the same time as any of the other exponents, or at least I do, because I feel like they lead in together very well. Now, is it going to be important for you to know that? I don't think so right now. I don't think we have to deal with fractional exponents at all. But if you had to deal with anything that had a fraction as an exponent, believe it or not, it's going to follow the exact same rules that I covered already. No exception. You'd still be adding powers, you'd still be subtracting powers, you'd still be multiplying powers. They would just have fractions on them. just like I just showed on the notes there. If I add 5 to the 37 and that whole thing to the 1 over 37, the fact that we multiply those powers still applies. Those rules will always apply forever, no matter what. There's no part of math where it magically changes later. So this is why I kept referencing pulling things out. Because what if it isn't perfect square? It isn't a perfect cube. What's the cube root of 32? I know the 5th root of 32 is a 2 because that was on the last slide. But what's the 3rd root of 32? Well, if I break it down to an exponential, that's 2 to the 5th. I have the cube root of 2 to the 5th now. All right. Well, every time I have a perfect cube, it can come out, right? We're doing cube roots. So if I have a cube, it comes out. Well, I have 5 of them. 3 of them are a cube. What about the other 2? Well, the other 2 just stay in. That's what's happening with that 2 times cube root 2 squared happening right there. That 2, this 2 just came off of that 2 to the 3rd. Realizing that I could have had another step in here just to kind of illustrate that better. But that 2 comes out because that 2 cubed came out. And then the 2 squared that we didn't use, that's part of those original 5, we didn't use them. And if you didn't use them, they didn't come out. Where are they? They're still in there. So a 2 can come out from this, but we still have 2 times 2 left inside. So you simplify it down. Everything on the inside that's left over gets multiplied together. Everything on the outside that came out gets multiplied together. We have 2 cube root of 4. So there's all the steps there. Do we love it? No? Brain shut downy? Okay. So let's do a bunch. Like how far up that is. There we go. Okay, I feel better. Very accurate meme right there. Okay, so given how these tend to work out, I didn't do a whole lot of problems on ones that work out perfectly because let's face it, we don't really do like 50 problems at a time. We do a couple and then you do a couple and then I tend to do those couple as well. But we don't have a huge amount of time to cover every little thing. So I'd like to do a bunch of perfect square roots, perfect cube roots, but we're just not going to have enough time. So that's why I have a very varied selection of problems here. And to be fair, I will say that you're probably not going to do a huge amount of cube roots in the future. Square roots are probably the most reasonable things to see at this point. But I did leave a couple of concepts. If you look at number 4 and 5, I did leave a couple of concepts off the slides because honestly, working them out is really quick and pretty easy to understand. So I didn't have slides for multiplying roots because it's incredibly easy. Well, you'll like it. It's great. So number 1, 144. That's a perfect square. Do you guys know what it's a perfect square of? 12, yeah. So we know that this guy would just be 12. That's it.
Why 12?
That's what I was waiting for. Okay, so.
Yes, why 12?
So here's the thing. It's 12 because 12 squared, 12 times 12 is 144. Now let's say you don't know that. A lot of people don't know these things off the top of their heads. So what you could do to break these guys down is factor tree. Now, factor trees, again, it doesn't matter how you do them, what you split them into, as long as you make sure you do your division carefully, get your numbers straight, then whatever you end up with is going to end up being correct. Now, this ended up being, let's count them, 1, 2, 3, 4 twos. So 2 to the 4th. You know what? I don't want to write it that way. Because I can write it that way, but I don't like doing it that way. I'll show you how I like to do them. Here's how I like to do them. I have a square root right now, right? I have a prime factorization tree. I know that any perfect square can come out of this radical, right? Any perfect square. Now, it doesn't matter if I can recognize 12, because when I get down to my prime factors, I can see anytime I have 2 of something, it's a perfect square, right? 2 times 2, that's a square. 2 times 2, that's a square. 3 times 3, that's a square. What I like to do is if it's square root, anytime I have 2 of something, I go ahead and circle it. Every time I circle it, I am going to pull out, hey, what's the square root of 2 times 2? 2. Hey, what's the square root of 2 times 2? 2. What's the square root of 3 times 3? 3. They all came out. They are all multiplied together because they multiply together inside to get this 144. So it makes sense that multiplication is still the thing, right?
Mm-hmm.
So what is 2 times 2? 4 times 3 is 12. So even if you don't know your multiplication tables perfectly, because honestly, I don't. I absolutely don't. I remember if you break out a multiplication table, I will know the diagonal. I will know the perfect ones. And mentally from there, if somebody asked me, hey, what's 11 times 12? I would think of 12 times 12 and I'd subtract 12. That's just what stuck. So, or I grab a calculator, I don't know. Whatever. But this is the nicest way I could find to do it. And it actually, if you do it this way, this concept scales up. Obviously, I like doing things that way, but this is a square root. So anytime I have 2 of something, I circle it. Well, guess what I do on a cube root? Anytime I have 3 of something, I circle it. Guess what I do on a 4th root? Anytime I have 4 of something, I'd circle it, etc., etc., etc. If I look at it that way, it doesn't matter what root I have. It's always going to work out. And that's why I don't like how a lot of these are taught in classes, because honestly, I feel like they could be taught easier. I basically just covered like 2 or 3 different lessons. All right. So we got number 1. How about number 2? Number 2 is square root of 4,500. Again, normally you're doing these types of problems. You're going to be doing basic ones like this over and over and over and over until it starts clicking. Again, don't have enough time, so I'm jumping right into big ones. Now, the nice thing of big ones, do I know what the square root of 4,500 is? No, I have no idea right now, right? And neither do you. No idea. So what are we going to do? Factor tree. How about splitting it into 45 and 100? And in fact, the 100, when I get to 10 times 10, how about I stop there? How about I leave that as 10 times 10? Because I'm doing a square root. There's 2 10s. I already know that's going to come out. We don't have to break it down into 2 and 5 and 2 and 5, and then pull out a 2 and pull out a 5, if I know that this is a perfect square. 45 is 5 times 9, which is 3 times 3. Hey, look, another perfect square. Okay. So what did I pull out? A 10 and a 3. But in this case, we still have that 5 inside, right?
Mhm.
Well, it's still inside. So we still have that symbol, and that symbol still has a 5 in it. So we can multiply these numbers together like we did on the last one. 10 times 3, we have 30. But that square root of 5, can't do anything about it. Now, what this ends up meaning, since we had a 10 come out and a 3 come out, this thing, the perfect square in there was the perfect square of 30. I would not be able to look at that and say, oh, obviously that's divisible by the perfect square of 30. I wouldn't be able to do that. Neither would you. So we find a way around it. Factor tree, anytime I have 2 of something, it comes out. Much, much
But
easier.
couldn't you tell by the 5 and the zeros at the end?
That it's divisible by the perfect square of 30?
Yeah. 30's right there, which leaves 15.
No.
Bro.
I mean, if you want to split hairs, the square of 30 is 900. So you'd have to be able to look at that and say, oh, this is divisible by 900, which I know is a perfect square. I feel like I should just say no in advance
Well, 9 is
to whatever you're going to say. No. You know, it's nice after those next 4 problems that I'm going to make you guys do yourselves. I'm going to call it good.
I can tell you right now that there's going to be a perfect square in number 3.
I don't care. It's a cube. It's a cube. Huh? Okay,
Let's see here. I'm just kidding.
you can.
I'm just gonna figure.
Now,
it
the
out.
tricky part is figuring out how to write that in a calculator. Let's see here.
I'm good.
Wait, go up a little bit.
I don't even know how to use those scientific calculators.
Let's figure it out. Let's see, we want to do a cube root. I'm thinking this guy right here. It's got an X and a root next to it. That X is probably referring to this guy right here. That's actually called the index. It's the index of the radical. So, okay, let's press it. See what, no, not that one. The second is like a shift button. So since it's the yellow part on there,
Okay.
that's what I got. Oh, God. Okay, so it does ANS, which means it's applying whatever number was already there to that. So I bet if I hit a 3 and hit that guy, yup, cube root.
And we're gonna be using this calculator for this.
Yup.
Oh, that's a wrap. But I don't have that on my calculator on my phone, so I'm not.
Yeah, that's fair. So
50.
here's the thing. Here's the thing. I spent $150 on this calculator at one point in my life. And you might notice, you probably don't, but you might notice it does not have that button anywhere. Anywhere. I actually have pi above that button.
But it's on there somewhere.
Well, that's the thing. I figured out eventually, like after I had my degree, that if I pressed a certain button and found it, yeah, like this thing 9, and I have to find I think I had to do it this way. I think I had to type it that way. Oh, you suck. The other way around, okay. Yeah, so eventually I figured out that it was a hidden button where I press this and then this 9. How am I supposed to know that? And then I had to figure out how to write it. So what I ended up doing, you know how I went over this example of, hey, this means that, where they had the fraction thing? The entire time I've used the calculator, I would do 125,000 and I would raise it to the power of 1/3. I would just turn them all into fractions every single time. It's completely ingrained in me. Now let's say you don't know how to do that. How we do? How we do? How we do? How about 1,125? What's 1,000? Well, it's 10 times 100. And I could break down to 10, but you can already see what's going to happen there. If I pull this one down to 10 times 10 times 10, I see, hey, I have 3 of them. Hey, I have a cube root. If I have a cube root, I need 3 of a factor. Well, there's 3 of that 10. 125, it's 5 times 25, which is 5 times 5. Hey, look, I have 3 5s. So I can pull out that 5. And if I pull out that 10 and I pull out that 5, that's where our 50 comes from. So 50 cubed is 125,000. Now, you might be able to eyeball some perfect square roots, but you can probably only eyeball a couple of perfect cube roots. Maybe 8, maybe 27, maybe 64, maybe 125. I don't know, but probably not a whole lot higher than that. 196. So we have this method. This method works quite nicely. And it, like I said, scales up. If I had a fourth root right here, then anytime I had 4 of something, it would come out. Exact same thing. Oh my God, how do we do number 4?
Okay, that's the same thing.
So the nice thing about multiplying roots is that, and I didn't have any that complicated on these ones, but anything I have, if I have 2 things multiplied together, if I have anything hanging out front, kind of like these guys, that 30 root 5 that we had here. If I had any numbers out front, I would multiply them together immediately. Just the things out front, multiply together. The things inside, those also multiply together. So this thing essentially is going to look like that. Anybody know what 18 times 5 is?
18 times 5 is. Wait, hold on.
Oh,
Let me try to do it again.
keep trying it.
40.
On the right track.
No. 90. 90, right? Okay.
Yeah, 5 times 18 is 90 because 5 times 10, 50. 5 times 8, 40. Slap them together, 90.
Why didn't I think about it? See? I
Yeah.
like to make things difficult for myself.
You could also do 5 times 20 is 100, and then 5 times that 2 difference is 10, and then subtract them.
Okay, let's do switch now.
Okay, that's fair. All right, so we end up with the square root of 90. Guess what we're gonna do there? It's a square root. Let's break it down. Now, one thing I could say is that when it's in the form 18 times 5 right here, I could have just factored that 18 and kept that 5 as if it was going to be in one of my factors as well. Because 2 times 3 times 3 is 18 times 5. So we could have just left it as is. Don't have to, but could. Well, what happens? There's a perfect square. It comes out. But we have stuff left over. We have a 2 and a 5. They stay in, they multiply. Anything that comes out multiplies together, anything that stays in multiplies together. Multiplies all over the place. So we have 2 times 5 inside, that is a 10. There we are, 3 root 10. Ooh. Look at that. Well, number 5, cube root of 2 times the cube root of 4, multiply the stuff inside together, cube root of 8. What is the cube root of 8?
4.
No, there you go. You're just gonna keep throwing numbers at me until one works.
Looks like I did.
Fair, not the only person I've seen do that. All right. So yes, it is a 2 because if you factor that guy down, you have 3 2s. So it is a perfect cube. How do we feel about roots?
They are yummy with breakfast and mixed with eggs. Come on, guys, that's a potato joke. Really?
They're okay, but they're not good enough for us to do on our own. I'm just kidding.
Well, tell you what. You try to do it alone, and we'll cover it. So we got 6 through 9. I did 5. You guys do 4.
Wait,
Let's see
hold
that.
up. I thought you said when you were
We
done with the
did
5
5.
classes.
What?
We did 5. All of us did 5.
Everybody together?
Yeah, we did
That
that
the
as a
argument?
team.
I feel like y'all are just trying to avoid these.
And then on top of that, I thought you said after the 5 class was over.
No, I said after the 4 I was gonna make you guys do.
Oh,
Uh,
well, since we already did 5, I mean, together as a team. We can do 4 together as a team too.
Yeah. It's much better, huh?
Just, you know.
Me and my ride don't get here for 15 minutes. You guys suck. Right, if you want to make it simpler, how about this? How about just do 6 and 9? Skip 7 and 8. Just do 2 of them.
Okay.
Does that work? Does that make us
Sounds
happy?
fair.
Does that make us happy?
Mhm.
I don't want to go to work tomorrow. Okay. I don't want to go to work in 10 hours and 45 minutes.
Wait, what did you say?
What?
What'd you say? You want to go to work in 45 minutes?
10 hours and 45 minutes.
Oh, okay.
Yeah, and more.
That's normally, if you had to do 2 jobs like that, back to that.
Hmm?
If you had to do 2 jobs back to that.
Yeah, I got off at 3 this afternoon. And then I wrote this class. And then I finished at like 5:15. To be fair, I should have taken the time after work yesterday to write this, but that's on me. How's everybody doing?
I'm stuck on the last one.
Huh?
I'm stuck on the last one, but I could just be. It's true.
Possibly. What'd you get for number 6? Yeah, okay, cool. Solid plan. Good job. What did anyone get on number 6? Man,
I'm trying to do it on my calculator, but I mean, I was gonna wait for the, I thought the last one was like the easiest one, so I was gonna wait for it, but I just got stuck on number 9.
Mhm.
And I don't even know if my answer is right.
Well, let's look at number 6 first. Square root 75. Factor it down all the way. It's a square root, so
Oh,
anytime you have 2 of something, it comes out. Anything stuck inside is stuck inside. We have 5 root 3. Now, I was curious how calculators were going to spit out for number 9. So I punched it into both the $20 standard calculator that you'll have on the test and the $150 I don't need this anymore calculator that I bought forever ago. So when you punch it into this guy, it just spits out a decimal, which doesn't really help us a lot, you know? And when I punch it into this calculator, what the hell? Now, I know how to interpret that, but you're probably not gonna be able to interpret that, right? So that thing's basically telling us it's the cube root of 4. So let's look at this. Now 108, I don't know what that is. So let's just throw a 2 at it. It's even, right?
Or
Cool. Which is still even, and we get 27. All right, well, 27, 3 times 9, and 3 and 3. All right. Well, it's a cube root. Anytime you have a cube root, you look for 3 of something. So we know the 3 comes out, but what happens with the stuff that we didn't circle?
it goes into the box.
Yeah, it stays inside. Now, it's still a cube root. What do we have? We have 2 2s. We're gonna multiply those guys together inside. So we end up with 3 cube roots of 4.
Wow.
And that's actually what my calculator was trying to tell me with the 2 to the 2/3. It was trying to tell me, hey, that's a cube root of 2 squared. So it does translate to the cube root of 4, but yeah, algorithms, they're a thing.
Well, I got 3 in the box. I just left the 3 out. The little, what do you call that little thing?
This thing,
Yes,
that is the index of the radical.
yeah, I just forgot to put it in there, and we,
Whatever. That's fine. This is the concept I want you to get.
I got all that right.
Okay. Yeah, that's not the end of the world.
Yeah.
This is like, if you miss writing that thing out down, that's like the king of partial credit right there. Like any math teacher who knows what they're doing is looking for not the right numbers, but whether or not the concept clicks.
Okay.
So if this concept clicks, I don't honestly care what numbers spit out over here.
Okay.
I don't care what number this is. It's just the idea we're looking for. Okay, so for once I actually covered exactly as much as I was hoping to cover, except for number 7 and number 8. Angry. Okay, hey, what's the answer to number 8?
No.
No, go a little further with that. Cube root 27, 3. Cool, that was it.
I was just guessing too,
Okay,
but I mean, I was trying to do the concept in my head of the 20.
but you've done it enough to the point where you see a 27 and you're like, 3 and 9 are in there.
Those ones are gonna be 3 if you break it down.
Now, if you want to see something really cheap and quick, I'm going to show you how to do number 7 really fast. Because we already know, hey, if I'm multiplying 2 radicals together like this, the stuff inside is going to multiply together, right? Well, 24 is 4 times 6. And I know that the factors are going to work out. Like, we went over this, like I totally could have just left that 18 times 5, right? Could have gotten away with that. What if I left this as 24 times 6?
Because it says mental load by default.
Yeah, also, I totally should have just done that. Cough, cough, cough. I didn't see the 4. I forgot about the 4. But yeah, if you guys had actually done the work and multiplied 24 times 6, it would have just been 144. It was literally these factors.
Oh,
Yeah, that's why I skipped those two, because they were quick. Those were the hard ones. I made you do it anyway. All right. So we good?
I am.
We are so good. Excellent, excellent, excellent.
Bye, see you. I'm gonna be, okay, so on Tuesdays, I'll still be on Zoom though,
Okay, I'll be here. Physically.
physically.
Mentally, not so much,
Have a
but
good night.
yeah, whatever. Have a good night, everybody.
Have a good night.
Maybe, I don't know.
Okay.